All right. This is that same artist that did the other painting we had up, and we're getting 3 more from him. This is that guy Create, who's the tattoo artist. Do you know who this guy is? It's another famous painter. He's the melting clock guy. Salvador Dali, yeah. See, she's the one you want to have on your trivia team.
Yeah.
All right. What we talk? Oh, we're talking about threads today. Oh my gosh, the world is ending for you.
Oh, no.
All right.
That's nothing new. Oh, it's not that bad, right? Is it bad?
All right. So, we on all the screens. So here's the scoop. I'm going to say blocking versus non-blocking. And let's just quickly give ourselves an example of some code. I'm just going to go ahead and comment out all of main for a moment so I can put some stuff in here. All right. So what I want to do here, oh, is it smaller than usual? All right. Give me a moment. Oh. Super Ninja. Is that closer? That better? All right. So let's assume that we're going to have our scanner. Scanner input is equal to new scanner. And we're going to build this guy using system.in. I'm already importing it up there. And then what I'm going to do is I'm going to say string line is equal to input dot next line. And we'll give them a little prompt before that, system.out.print. Enter something. All right. And then we'll prove that we got it. System.out.println. We'll just echo back whatever they typed. All right. Creator scanner, prompt them, read something in, spit out what we read in. Nothing special, right? All right. So do that. We'll type in our super secret blah blah. And there's the output. Okay. Nothing new there, right? So now what I'm going to do, I'm going to say while true. And I'm just going to say int count is equal to 0. Inside here, we're just going to say count plus plus for no good reason. Okay. How long does this loop go on for? Forever, right? So what am I doing in there? I'm starting off at 0. It's going to be a 1, then a 2, then a 3. What happens when it gets to 2.1 billion? Goes to negative 2.1 billion. Why? Yeah, it's a bit overflow. So this is something you might be talking about or already talked about in 325, right? Okay. So I promise you it will. It'll roll back. It'll roll back around because of how two's complement is stored. Okay, you've done two's complement? Who? Oh, computer architecture, organization, whatever. All right, so we've already covered this is a loop that goes on forever. What are we doing inside this loop? We're just going to increment count. We've already decided that count, once it hits its maximum number, it goes to the minimum number, starts counting back up. So it will count forever as well, right? This won't crash or anything like that. So when I say run here, from my perspective, oh, it's already giving me an error. Let's see. So I'm going to say while int blah is equal to 10, while blah is less than 100, and then I'm just not going to change blah. All right. So instead of saying while true, which allowed the compiler to determine that, hey, you're never getting past this line, I just made a Boolean expression here. And since I never change blah, it'll go on forever. All right. That expression will never be false. So my program's still cooking, no problem. All right. But I haven't got to the line that says enter something or read it in or anything like that. Why? Because this code right here is blocking us from getting to this code down here. Make sense? Okay. Similarly, if I go ahead and stop this, we can go ahead and have a system dot out dot println hello world. I know I missed the letter there. So all that, well, really, this code right here blocks us from getting to this line. Also blocks us from getting to this line. So when I run this, our program is paused right here on line 17. Well, really, it's paused on line 18. It's waiting for us to type something in, which means that any other logic we want our program to accomplish right now is not being accomplished because that line of code does what's called blocks. Okay. Now, sometimes we might want to have stuff happening in the background, right? Take your video games, for example. You're sitting there maybe solving some puzzle in a certain part. You still want to have the monsters and stuff running around in the background and feel like you're in a living world or something. Well, if it's waiting for you to click on something, and that's the only way that other things can move around, the whole world will pause while it's waiting for you to give your feedback. Just like what's happening right here. Okay, we can't get to the next line of code until we finally type something, and then it completes those next lines. Once we press enter and we allow this line to actually complete, it can finish going. All right, so this is called blocking code. Blocking code pauses the execution of the program until such a time that the code unblocks. Usually from human interaction. Non-blocking code is code that does not require human interaction or other external interaction, and therefore allows the program, let's just say, to keep going. Sometimes that's fine, right? But every now and then we want to have more than one thing happening at once, or at least seemingly happen at once. Okay, so this kind of becomes that computer architecture type thing. It's less of a thing anymore because now we all have multi-core processors in our computers, right? So most of you have at least 2 cores, probably most of you have 4 or more cores. I think this thing has like 32 cores, something stupid. That seems just unnecessary, to be honest. Because more cores doesn't necessarily mean faster. But in any case, it does mean the more things you can do at once. All right. So the idea would be, I probably use this as an example, but if we get a big snowfall and one of you can shovel snow at speed 10 and the rest of us in the room can shovel snow at speed 7, who do we want to have clear the snow at on campus? The rest of us. Because even though as individuals we're slower than that one person who's a turbo shoveler, right? As a team, we're going to get the campus shoveled more quickly because we can split the work up. Make sense? Okay, that's the mentality between for multi-core processors. From our perspective right now, a multi-core processor effectively says more than one thing can actually happen at once. We go back in time to when we only had single core processors. And this is really where this idea of threads came from. When we had single core processors, more than one thing could not actually happen at once. We were just reliant on our computers being so fast that we were convinced that more than one thing was happening at once. Okay. But in both of those situations, because of how software runs, we can still have blocking code. Even though your quad core laptop might be capable of doing 4 things at once, if we run this program and we hit that line that's waiting for the user to enter in something, those other 3 cores are not going to be able to help you in your current running program because your program blocks. You have to have some way of letting the operating system know that I have some other stuff that I might want to get done in the background. Help me out here. And either schedule for my single core processor to trick me, to fake me out that more than one thing's happening at once, or somehow schedule these other threads on one of the other cores so things can get done. All right. Now, we do have to think about, though, whether or not blocking code is important. So, for example, I definitely want to make sure that this line completes before I execute this line, right? I don't have a value inside of line until the user types it in and presses enter. In this case, blocking is important, okay? But I wouldn't mind if that line went ahead and fired while I'm waiting for the user to type something. It's not that that non-blocking code versus blocking code. It's not that one is better or worse than the other. It's what's the right tool for the job. Go ahead.
Yeah, that you said that more cores doesn't necessarily just that but yeah, for video games, does that still mean that? Because it's like it means more. I mean, it means that it doesn't have to tribute as much as actually.
As long as you actually have more than one thing to do.
Yeah.
So like, if we're, like how many people does it take to change a light bulb? It takes one person to change a light bulb, and we have four people in a quad core processor. We have 4 people willing to help change this light bulb. Okay. But we have one person who can change the light bulb at speed 10. Okay. Versus 4 people that can change the light bulb at speed 8. Who do we want? Do we want the single core processor that can change the light bulb at speed 10? Or do you want the quad core processor that can change the light bulb? Each core can change the light bulb at speed 8. You want the single core because you want to have that light bulb changed as fast as possible. And that's not a job that requires more than one core to accomplish it. Well, so you asked the question about video games. Most of our modern day video games do have more than one thing happening in the background. So multiple cores will almost always be better modernly than a single core. Now, having said that, there is something to be said for having too many cores, which is kind of where things get interesting with like these new server-based super core type of machines, which might be great if you have a server that's having 500 users connect to it at once. Then having multiple physical cores might be a good thing because now you have 30 cores that are all trying to trick the end users into they're all getting CPU time. Okay. But typically each of those cores has a speed associated with it. So maybe it's a 2.4 gigahertz processor, and that might mean something based on whatever architecture you're on. But if we're comparing the same architectures to each other, a 2.8 gigahertz processor is faster than a 2.4 gigahertz processor. It can do things, it can do more instructions per second. Okay. Well, so if you only have one thing to do at once, change that light bulb, you want that 2.8 gigahertz processor all day long. Okay. But you're shoveling snow, converting videos, things like that. And that's the main purpose you use the machine for. The more cores, the better. And you're willing to give up some of the top end speed on a per core basis to have pretty fast across a whole bunch of cores. That makes sense? But for most normal uses, more than 4 or let's call it 8 cores is probably overkill. Okay? Unless you're really getting into graphics type stuff, Or like I've mentioned in here, I run a lot of virtual machines. So if I swipe there, there's Windows 11. So I have a whole nother operating system that could be running at the same time. I have it paused right now, but that operating system has cores dedicated to it. So I can have, an 8-core setup with 16 gigs of RAM for Windows 11 and still have 22 cores left over for my Mac, let's say, or running Linux or whatever. So when you have resources you want to divide up amongst a bunch of different things, that's where something like that starts making sense. But if you're just running Windows on a machine, I would say really anything more than 4 cores today is probably overkill. 8, you're probably not wasting your money. You're giving yourself a little bit of future proof. Anymore, some of the laptops are starting to come out with 8 cores, but you have kind of like 4 or 6 performance cores, and then 2 efficiency cores that use less electricity. So they're the ones that are cooking when you're like checking email and stuff like that, and you're don't really need a whole lot of horsepower. So some of it's more of an efficiency thing. It's becomes even more interesting at the smartphone level, where those efficiency core things have been around for a while to try to save your battery life. All right. But the idea is sometimes we want to have more than one thing happen at once. Sometimes we might want to at least fake having more than one thing happen at once, which single core processors at the general purpose computing really don't exist anymore, but they did, 12, 15 years ago. But threads are our way around this. Okay. Before threads, we had, and this is something you'll learn in the systems programming class, we had multi-processes. So when you're in 350, which is operating systems, you'll talk about process management by the operating system. In 450, the systems programming class, you'll actually write software that deals with multiple processes. We're going to look at the more modern approach to this, which is threads. So in any case, let's go ahead and take a look at this. If I want something to happen in the background while that guy is waiting for human beings to do some processing, I need to use a new mechanism. And that mechanism is going to be called a thread for us. All right. So let's talk about threads. So a thread, a modern day approach to allowing the OS to schedule more than one task at a time, either on a single core CPU, or it might even be just on a single core of a multi-core CPU, okay, where it's trying to fake you out. If you're using one of your 4 cores for your software, a thread would still allow that core to trick you into thinking more than one thing was happening at once, so it wasn't technically blocking. Schedule more than one task at a time on either a or a multi-core CPU. So multi-core CPUs, the process scheduler or the thread scheduler on the operating system, it would take advantage of cores that aren't currently busy doing things and allow one of your threads to run on that. So you're actually getting extra throughput. Okay. All right. So that's what a thread is. Now, how are threads accomplished? Well, we need to look at something called interfaces. An interface in Java is a set of requirements that implementing classes must meet. And let's go to the, let's see, we'll do Java runnable. One naming convention we will see with interfaces in Java is interfaces tend to have a able at the end of them. All right. Just a naming convention, nothing important, other than might be how you can identify one in the wild. And we're actually not going to go very deep into interfaces, and I probably won't test you over interfaces specifically, but I need to introduce interfaces in order for you to understand where threads are coming from. Okay. So the idea of runnable, this guy sets up a set of requirements for any class that's going to implement that interface. All right. A good example might be most of your machines have USB ports in it, right? And there's all sorts of different devices that are USB compliant, right? You got jump drives, you got mice, keyboards, blah, 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 right? But they all have to adhere to a standard that talks over a USB interface. In order for that one port that came on your laptop over multiple years that USB's been around, any device that's going to plug into that USB port has to have at least a baseline set of requirements in order to speak over the USB interface. Make sense? That's what an interface is. This is the software version of that. Okay. So runnable is the interface that threads implement. And it just so happens it's a fancy schmancy way of saying you have to have a single method called run in order to be considered runnable. All right. Okay. The bar is low. All right. But this is very similar to what we ran into with println expecting anything that's an object to have a toString method. Right? Because if something implemented, something is an object, then the rest of Java knows that I can call toString method on that guy because he will definitely have one. Because somewhere in his lineage is object, which has toString. All right. That's not technically using an interface. That's through inheritance that it's guaranteeing we have that. But in this case, we're saying we don't have any sort of, so kind of an important thing with implementations or an interface. This guy does not define an implementation. Whereas toString in object does do something by default, right? That's the dude that returns the string that looks like the crazy memory address thingy, right? That's what the default version of toString does. In interfaces, when we define it, so for instance, here in runnable, it says you have to have a method called run that returns nothing. If you're going to implement this interface, you have to write that. But there is no default behavior. An interface does not have an implementation. It sets up a standard that you have to adhere by if you are going to implement that interface. Follow the rules of that interface. If you're building a USB compatible mouse, you need to make sure you follow all the USB rules so you can talk to the operating system through that port. Make sense? Go ahead. If that class implements runnable, which we're going to see here in a second. You haven't seen an example of that, but I promise you threads do something called implement runnable. Runnable is an interface. So runnable is a standard. Runnable is an interface. It's a standard that says, if you're going to implement this guy, you must have a method called run. So if we cheat and look ahead a little bit, and I say Java thread, which is in just java.lang, and we scroll here, we see that this guy implements an interface called runnable, which means that when we scroll down, we should find in here a method called run. He had to write that method. And the default run method for a thread does nothing other than exist. All right. Which means that if we're going to write a thread, something that is a thread using inheritance, we probably want to override that run method so that our threads do something. Make some sense? All right. So really what we're doing is we're looking at kind of the lineage here. We have interfaces set a standard. Things that implement those interfaces follow that standard. Okay. Just like the USB on all your laptops. If I have a jump drive and it works in my laptop and I give it to you and you plug it in, it'll work in your laptop. Why? Makers of that jump drive follow the interface for USB, the rules that it takes to talk over USB, at least the bare minimum. They might have some extra fancy schmancy stuff they do over there. Okay. But the default is they know how to talk over USB because somewhere out there, there's a standard for USB 2, USB 3.1, so on and so forth. All right. So thread is a class. This guy's a class that inherits from objects. So he's a top level class, right? There's nothing in between him and the most generic thing. But he also does something called implements an interface. What interface? Runnable. And that means that he will have a run method. Furthermore, it means whoever wrote thread had to write a run method. If you implement the runnable interface and you don't write a run method, it'll scream at you and say, look, you have not implemented the runnable interface. You said you were going to right up here. So if I, let's just show the error real quick. So I'm going to create a new file. I'm going to call this guy my worker B. All right. So this is workerb.java because I kind of think of threads like that, right? We got these little worker bees. We want to run off and do some other things while I'm focusing on the center thing, right? Okay, but they're non-blocking, so they're off. They've doing their own thing. All right, so we'll say public class worker B. Now, just for the sake of argument right now, I'm just going to throw in here implements runnable. Now, the reality is as a Java developer, you will probably not actually implement interfaces all that often. It's not really a common thing. In fact, if you're writing your own code in Java, you actually may never have to implement an interface because you could just say, oh, well, I'm going to write some code that does this. I'll just make sure I put a run method in there. I don't need something like this to police me and scream at me if I don't. Make sense? So sometimes as developers, we're like, look, I know enough. I don't need a speedometer in my car. I'll just kind of wing it. Okay. Not, I know how fast I'm going. Right. Okay. So not implementing interfaces means no cops on the road, which maybe you're a fan of, but, nobody to scream at you when you break the rules. All right. But if you're in a larger, software development group where you are adhering to some standards and everybody's writing, you have your projects you're working on, somebody else has their projects, but you all have to be compatible with some level of standards. You might then implement some interfaces that will police that you've written all the methods you have to write to be compatible with that standard. You might still have bugs, right? Your logic might not be right, but at the very least you've met the requirements of trying to meet that standard. Go ahead.
Is there ever a time where multiple interfaces?
Yeah, you could just put commas after runnable and say I'm gonna implement trying to come up with even another interface. There's really actually tons of them, and for some reason I can't come up with another one right now. But in any case, there's comparable is another one. So if you want to write your own kind of a Boolean class where you can compare two things to each other, you can implement the comparable interface, which is going to tell you to write a certain method. I think the method is compare to, that must return an int. It returns an int -1 if the calling thing is less than it, a 0 if it's equal to it, and greater than 1 if it's greater than it. So you can turn any of your classes into compatible classes for allowing you to compare them to other things through the generic compare to function by implementing comparable. But nothing says I can't say, well, I want to follow the rules of runnable and comparable. So now I'm being doubly policed. Make sure I meet all those requirements. And if there's overlap, that means I need maybe comparable, let's say, must have a method called void run. Well, if I don't implement them, both of those interfaces will scream at me, right? but I have to implement a single one that meets that performs the logic of whatever both of those are, but it's going to tell me what I have to write. All right, make some sense what interfaces are for. Okay, much more about kind of group standards. That's where you're probably going to run into them in the wild. All right, but it just so happens that Java's built-in thread class implements runnable, which means it has a run method. All right, that's the punchline of this whole thing. But we want our guy. We're not actually going to mess around with the interface here. We were just seeing what's under the hood. Instead, we want to say, you know what? I want my worker bee to actually be a thread. So we're going to say this guy extends thread. So now he is a thread. Make sense? All right. Now, if I don't do anything else, this guy will be a generic thread that does nothing. So I can just go back out to main here. Let's just get rid of these dudes. No, thread came with run that does nothing. Yeah, I got it. It's just useless. Okay. Say, yeah, same thing. Our worker bee is a thread. Thread already has a run method that we saw down here. We don't know what it does, but I'm telling you it does nothing other than meet the requirements of implementing runnable. Okay, so here's our, where's the R in the alphabet? There it is. Nailed it. All right, so there's run. Threads already have that. Okay. So otherwise, so you either write your own or this method does nothing and returns. Very lazy thread. Okay, but still a thread. So I'm going to go ahead. So my worker bee is a thread, and I am not going to differentiate myself from threads at all. Should not happen. Okay, but technically legal. All right, this class did not need to be made if I'm not going to actually write anything unique in here, but we're going to still make it, which then allows me out here. I'm going to say worker bee WB1 is equal to a new worker bee. And I'll say worker bee WB2, WB3. So I've created 3 different worker bees. Now, we know that each of those worker bees has a run method, right? We know they all have a run method, but unfortunately, that run method is not something you're going to directly call. The reason that we are implementing the thread class over here, the reason we're saying worker bee, we want you to be a thread, is there is something magical about the thread class built into Java. It knows how to intervene with the operating system and actually create that thread of execution. Okay, it's under the hood kind of stuff that actually tells the CPU, probably through the virtual machine in this case, I need you to schedule this separately so this is non-blocking. It's doing some stuff that as Java programmers we don't have access to. Make some sense? Okay, therefore our pathway to get that functionality is by extending the thread class. We get that special ability. Okay, so we actually don't call run directly. Instead, we call a function called start. If you look at the documentation here, you'll see that we have a function called start here that says causes this thread to begin execution. This is the magic, right? The Java virtual machine calls the run method of this thread. So it'll call that run method, that thread implemented that does nothing, that we probably should re-implement to do something. Make sense? But ultimately, we're going to tell our thread to start. which will perform the operating system level magic and ultimately call our run method as the thing that that thread does when it's started. Okay. So right now, worker bee is a thread. We haven't implemented anything extra because we suck. And we don't want our code to actually do anything useful yet. All right. So I'll create my 3 worker bees. I'll tell each of them to go ahead and start. And we're going to tell each of those guys to start. All right. And we will have 3 threads that are running. Well, technically we have 4 threads because main runs in its own initial thread. So modern day applications, when they execute, they run inside of their own thread of execution, which is actually for security reasons, so that your program can't necessarily take over the rest of the operating system. When you get into, have any of you taken a security class? Okay. Well, you maybe heard of something called the denial of service attack or distributed denial of service attack, DDoS. Terrible, right? Ultimately, what does that do? Denial of service. Anybody know how denial of service works? Go ahead. Well, that's its goal, right? Yeah. Go ahead.
It tries to do with service so many users that
Yeah. So when we talk about a server, what's a server? A server is a computer, right? It's a computer that's sitting there. So let's just say we're dealing with www.google.com, which is actually kind of an array of servers, but let's just pretend it's a single computer. Yeah, single computer, right? So that computer has only so many processes that can be running on that computer at one time. All right. It's a modern day Linux machine. It's probably something like 4.2 billion processes. If a little bit older, it's probably 65,536 numbers that we've heard before based on the number of bits, right? That's how many processes that can run. What's that dictated by? Well, it's dictated by the process manager of the operating system that's keeping track of it as a short or an int, right? If it's an int, and it's an unsigned int, we can hold 4.2 billion, which is 2 to the 32nd power, 32 bits for an int, number of processes, because that's what we can count to. Any higher than that, we lose track and it loops back around, right? Okay. So it just has to do with the implementation. Well, for every process, that guy's getting some CPU time. So as we have more and more and more and more processes in our computers, now we're right back to this multi-core thing. You know, the more we're reliant on our processors to handle that, to fake out the end users that we're doing a bunch of stuff at once. The more users you have, you know, for all of us, we're pretty much the single user of our computer, right? We're not serving anybody else's needs. We're the single user on our computer, which is why something like a 4-core is plenty. Okay. 8 cores overkill, but maybe in the realm of reasonable, let's say. But if you're running a server, for instance, how many simultaneous people are using google.com? We'll round down and say a lot. Okay. So much more than one. All right. More like multiple millions. All right. And so they have an array of computers because each of those computers has, you know, probably dual or quad CPUs in it, each one with, let's just say, 48 cores. All right. So roughly, let's say each computer has 200 cores that it can distribute amongst its people. So let's just say it's a single computer. You have 200 cores. So those 200 cores are servicing the up to 4.2 billion processes. A denial of service attack, what it does is it hits port 80, for example, which is the port for the web server rather, at Google. And it just keeps opening up GET requests, searches. I want to search for this. I want to search for this. I want to search for this. Infinite loop, right? And for each of those, a process gets created. Until what happens? The operating system runs out of processes. And when it's at 4.2 billion processes, what happens? Well, when you try to create the next process, it's probably going to die, but the damage is done, right? So fine, you can't do another search. But what's the other problem? The system administrator can't launch a terminal to kill off all your processes because that terminal itself will be a process. Okay, so he can't launch it. All right. Well, so what was the original fix? The original fix was, oh, well, we'll just block that IP address. Step in, distributed denial of service. We'll hit you from a whole bunch of angles. Can't block everyone. All right, so that's kind of the punchline. The human workaround is when the OS first launches, just open a terminal. Now you have a process for the terminal. You can just do a kill star on anything that's on port 80. But that's effectively what denial of service is. Almost all of these like hacker type things, when you actually get to the bottom of it and realize what they are, they're very trivial. It's an infinite loop. It's an infinite loop. We'll write a loop that just keeps opening up sockets to google.com port 80. We can probably write it in 10 lines of code. Well, we only have 5 minutes left, but I mean, it's not a hard program to write. That's what I'm saying. It sounds like it's this complex thing, but it's really not. All right. So in any case, right now, if I run this program, my worker bees have a run method that we didn't write, that we got from thread. That run method does nothing. They also have a start method. That method's the guy that does the magic to actually start the thread that the operating system knows about, so it can schedule it as a separate entity. All right. So our program right now literally will do nothing. I run it. First thread launches, 3 more threads launch, program ends. All right. We've just written a multi-threaded application. All right. Now let's step it up. All right. So now what we're going to do is we're going to say, hey, it was better spelling than my last time. Okay, we're going to say public void run. All right. And this guy is going to say, I am a worker bee. All right. But we call run. We do a system.out.println. I am a worker bee. That's it. One and done. Go back to main. We'll hit run. We'll see I am a worker bee 3 times. Well, Java's not slow. It's online GDB that's slow for launching it. I don't think it'd be really any faster from this website. I mean, the Java and C++ will feel just as fast if you're sitting doing it locally. So now we just saw we had 4 threads there, I promise. Okay, and actually, if you know, let's go back to main here. I'm gonna go ahead and say system.out.println. I am main. Run that guy again. It's possible these guys run slow enough that main actually happens third, but it's possible. Yeah, there's main in the middle there. So 2 of our threads got a word in edgewise before main was able to sneak in, showing us that it didn't block. And then our last worker bee stepped in. Right. But it's because behind the scenes, the operating system is scheduling those threads for CPUs, and IO writing stuff to the screen is slow. I think I've shown that at some point where you write a for loop that just counts, it's super fast. You write another for loop that counts and prints to the screen, super slow, because writing stuff out to the screen is a very expensive task. So now let's go into our worker bee, and why don't we say while true, All right, well, true. So now what do our worker bees do? They sit there and say, I'm a worker bee forever. Okay, so we'll go ahead and hit run. So there's those guys cooking. Got a zillion of them. All right, they're running forever. Now, if we were, eventually this will time out. And the reason it'll eventually time out is our main thread has actually ended, right? We've hit, because this line did not block, right? Somewhere way up high, we have I am main. So we finally hit the end of main, this program ends. One of the reasons that threads are our modern way of doing things is a thread is owned by the parent process. So all of these threads are children of our running program that's main. Okay, and they're actually sharing the CPU time with that guy. As opposed to the older way of doing this, which is multi-processing through a, and you've actually seen this before, it's through a system called fork. You've seen when I've given you a link to something, you can fork that repository. Okay, you know, that means create a duplicate of that. So in systems programming, you'll see how fork works, but you have to be very careful to enunciate, because when you're talking about child processes and forking, things become very, 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 you got to be careful. All right. And then was one time having a conversation at a restaurant with some sysadmin guys. Well, and it wasn't even about that side. It was reaping. We created a reaper process to kill off children. Right. So you know, you start off by forking a whole bunch of child processes, and then you're reaping, killing off those child processes. And these two old ladies that were 2 tables over were not happy. Okay, because we are plotting something very uncouth. All right. So in any case, now we have threads. What we'll do next time is we're going to make our worker bees do something very specific. Okay, we're going to teach our monsters how to be a worker bee. And maybe each time through, maybe we'll pause for 4 or 5 seconds, and then we'll maybe roll the dice, and a rat will decide, should I take an exit or not? So all of a sudden you might be standing in a room and a rat wanders in, right? All right. Questions, comments, concerns, bribes. All right. I will see everybody on Wednesday. Here, I'll put a link to this code up, even though right now this code doesn't really do anything helpful, but it's a thing.
Would your, I don't know if this how this works, would your cores like overheat eventually? They kept running out over.
Well, your modern day computers usually have sensors in them, so your computer might protect itself before it got that hot. I'm actually interested. Does this show me how many cores this computer has?
If you click more in, mine has 4, and then it says 4 efficiency. It's like you were talking about.
I don't see the
Well, it looks different.
maybe system report.
Yeah. 8 performance and 4 efficiency.
Where?
Total number of cores on hardware under chip. It's on
Oh, over here?
Yeah.
Oh, under chip. Total number of cores 12. So 8 performance cores, 4 efficiency cores. And then our graphics has a zillion cores. 38 cores.
Is there a maximum
I wonder
number of,
what
like
mine is.
graphics cards of like how many cores you can have?
No, in fact, that's usually the what they say for each new one, because the cores in GPUs are all they're just little floating point coprocessors. They just do math. So You know, they'll have 1024, 2048 cores, just a whole bunch of like, you know, that way each of those cores can
Individual bits.
pick a polygon or whatever and, you know, someplace on the screen.
I guess unless you can just keep on increasing the number of cores pretty much infinitely. with that
Yeah,
one.
yeah, assuming, you know, because now you start getting into things like heat and being able to fit it on the processor die, the GPU die.